Thanks for the intro. Yeah, so my name is Gian Merlino. I'm a committer on the Druid project. I'm working on it for about 2 or 3 years at this point, and I'm also a co-founder of Imply, which is a company that's based around Druid. We offer an analytics platform that's built around Druid, all open source stuff. So today I'm going to be talking about the Druid project, how it started, what motivated it, do a little bit of a demo of Druid, of metrics stored in Druid, talk about how Druid works, and then talk about deploying Druid. And this is, I guess, 25-minute talk, so near the end I might start going kind of fast. So I like to start with this slide. It's really important to know what you're trying to do when you start building something. So when we started building Druid, which is a solution, we had a problem. And the problem that we had, that we were building Druid for, was to power an ad tech analytics product. So it was a product where data that's coming in as impressions and clicks from online advertising, and we wanted to do slice and dice analytics and reporting on that data as a sort of a cloud product for folks in the advertising industry. So this was about 2011 when Druid got started. At the time, there was a lot fewer analytics tools than there are today, and we felt the need to build one because we had these set of requirements that existing tools weren't really meeting. So we wanted something that could be scalable. At the time, we were definitely not doing hundreds of billions of events per day, but now that Druid cluster is, that original Druid cluster. There's many more now, but that original one is still pretty big. We wanted it to be multi-tenant. Again, at that time, it wasn't hundreds of concurrent users, but now it is. We wanted it to be interactive, low latency queries. So the target there is less than a second for most queries. We want to be able to power a UI where people can click around and see things happening as they're clicking. And that's always been there. It's always been low latency. And we want to support real-time, low latency ingestion, which was not there on day one, but was there before it was open source. Druid was open sourced in 2012. Again, the first lines of code written about a year before that, and open sourced about a year after it got started. It's currently got over 150 contributors from 100 different organizations. Most people using it are using it to power analytic applications and dashboards. And so what I mean by analytic applications is applications let you slice and dice and drill down through your data, get reports, stuff like that. And by dashboards, I mean the stuff that you think of when you think about dashboards. Just pretty pictures, graphs, updating in real time, that kind of stuff. One common thread about things that people use Druid for is it can unify historical and real-time streams, or historical and real-time event streams. So that means a couple things. It means both the system can actually store data going back for whatever retention you want. It's not just for recent data. It can also do streaming loads and batch loads. So you have flexibility in how you store data and how you load data. Again, most people are using some sort of slice and dice, drill down motif to the application they're building. And as far as what it's used for a lot of people using it for behavioral analysis because we support distinct counts, retention, funnel analysis, that kind of thing. Also exploratory analysis, just asking questions, getting answers, and root cause analysis, trying to find what caused some anomaly in my data. This is just a bunch of logos of people that are using Druid in production. This is my other co-founder, Fangjin, went through the Druid Powered By page and painstakingly typed them all into Google and put them on a slide. It looks cooler this way than just a Powered By page. And this is the data model behind Druid. This is how Druid thinks about your data. It thinks of your data as event streams. So this is the SF metrics meetup, and that's it matches really well. So metrics are a stream of events. If you have time series metrics, that's from a counter or a gauge. Your stream is just observations of that counter or gauge. If you have metrics that are individual events happening, then the events are just events happening. So we handle both of those, both the sort of periodic measurements and just streams of events happening. Every row has a timestamp, some dimensions, which are attributes that describe that row. So for the original online advertising use case, attribute to be like what site the ad was shown on, what the ad was for, and what the image was for the ad. For server metrics, it could be the host name or what the host type is, stuff like that. And then measures are numeric things that we're going to be measuring and aggregating over. That data is split into segments. And so every segment in Druid has a few million rows, and there's time locality. So all the data for the same time is located in the same segments. And that helps us do queries faster. So that brings us to the Druid query path. The Druid query path is how it does queries. So it's a 5-step path where first it prunes the list of segments. So a cluster that has data loaded in for years might have thousands of segments or tens of thousands of segments. the first thing it does is that prunes based on whatever parts of your filter it can use to do that, which is normally time, and if you're using a secondary sharding dimension, another column as well. But usually time. Most queries are for the past day, past week, something like that, and we can prune that list of 10,000 segments down to 100 segments or 50 segments. Then we filter using indexes. So the indexes in Druid are currently all bitmap indexes. We're working on other types, but they're currently all bitmap indexes. Then we scan, we iterate through the rows matching that filter. This is done on the data nodes. We aggregate on the data nodes. So we read just the columns that are relevant to your query on the data nodes. And the data nodes build their own partial aggregates. Then the data nodes return results back up to the query node, which does a merge. Some real world numbers. These are numbers from the original Druid cluster that we originally worked on. That cluster comprises over 100 petabytes of raw data. That's not actually 100 petabytes in the cluster because that data has been compressed and summarized. I think in the cluster it's maybe not quite a petabyte, a few hundred terabytes. It's a few hundred nodes. The cluster is currently ingesting 3 million events per second. And average query latencies are half a second, and 90% of queries are done in less than a second. The long tail, the 99th percentile, it gets kind of high. It gets to be like 10, 15 seconds, but the majority of queries happen in less than a second, which is what we're shooting for. So let me do a demo now, just to show the kind of apps that I mean when I say analytic apps. So this is a demo that we hooked Druid up to GitHub. So we have a bot sitting in EC2 somewhere that's reading this GitHub API where you can see what's happening on GitHub, just get a stream of events, and we read from that and push those into Kafka, and then we're loading from Kafka into Druid. How many guys here are using Kafka? Cool. Kafka's cool. I really like Kafka. Druid works really well with it. So we're pushing those events into Kafka and loading things from Kafka into Druid. And so this is just a time series of events over the past day. It's kind of boring, but we can see something more interesting, like what are the biggest repositories over the past day. And everything I do, so the top one is a Pokemon Go related thing, which is not super surprising. Let's see what languages are written in. So let's filter on that. And I want to see, look, it's a Python. That's cool. Python's a good language for Pokemons. I can see who's contributing to it. So filter on that. I want to look at users. Looks like it's getting a lot of contribution from a lot of different people. That's cool. I can also do stuff like, let's look at the Druid repository itself. So I'm filtering on Druid, and this filter is using an index on, so we build an index on every attribute. So this is an index on repository on all the data nodes, which is what makes these queries so quick. So this is who's doing stuff today in Druid. That's cool. I can look over the past 7 days. I can even take someone that did stuff in Druid. So this is Fangjin, who's sitting over there. See what else he's doing. Other repositories. Just Druid. Good job, Fangjin, staying on message. So yeah, this is the kind of stuff that we can do. It's all sort of slice and dice, drill down, looking at your data from different angles. And most views that you see here are generated from maybe a half dozen Druid queries. So these tables on the side, each one is a Druid query. This big table in the middle is one Druid query. And actually, when I type in something into this filter thing, so when I type in myself to filter for myself, that's another Druid query that does the autocomplete. I got another view that is system metrics. So this is, we hooked up Sensu into Druid. So we have Sensu running on our boxes. We just installed it a few days ago because we thought maybe it'd be good to actually monitor our stuff and make sure it's working. So I do stuff like see the CPU time being spent on instances that are being used and what's happening. So let's look in the last hour. So in the last hour, CPU use has kind of gone up on these data nodes while I've been doing the demo, and that's not surprising. It's because I was doing a demo on them. It hasn't gone too high, though. It went up to 7% average. So they weren't working that hard doing that demo. A few other people could have been doing it at the same time. OK, let me go back to the slides. So yeah, so those are the kinds of things that you can do with Druid, and also that UI is something that we make it imply. It's open source. You can go to our website and download it. It's called Pivot. Everything we make is open source, so feel free. I'm going to talk a little bit about what I think Druid's advantage is. I'm not going to talk about its disadvantages, but that's for the Q&A. So if you pay attention, you'll be able to ask me questions that I can sort of hem and haw to and be like, oh, Druid's not too good at that. But I'm going to talk about what it's good at. So versus relation. So look at, these are some other things that people often use for the kinds of problems that Druid's used for, these slice and dice query problems. People use general purpose relational databases like MySQL and Postgres. They use general compute engines like Hadoop and Spark, and they use key value stores for storing metrics like HBase, Cassandra, OpenTSDB, which actually is just using HBase. So against relational databases, or general purpose relational databases, our big advantage is that we are column-oriented, not row-oriented. And we're built-in distributed, as opposed to a lot of these traditional relational databases are not really built-in distributed. So it's difficult to manage partitioning with them. You can sort of shard manually, but we have a lot of code in Druid dedicated to doing the sharding automatically, balancing data automatically, pruning queries automatically that you don't get if you're using one of these databases and building it yourself. Also, insert rates tend to be slow. In Druid, we do real-time inserts in a particular way that I'll go into in a different slide that lets us do very fast inserts with minimal checkpoints to preserve transactionality. Whereas most of these databases do transactions that are much more fine-grained, and that reduces the insert rates. Also, the row orientation makes queries just end up being slower, because you have to load all the data for row, not just the columns you're reading. General compute engines like Hadoop and Spark. You have some sort of computation layer like Hadoop, Spark, Presto as your compute layer, and then you have some storage, which is usually for those systems HDFS. What we see as our advantage against those guys is that most of those is difficult to load streams because you're using HDFS as your storage. There's no real great story about what the way is to load data into HDFS in a streaming way. It's also the overhead in separating the compute and storage layer can make queries slower. And then finally, key value stores. These are pretty popular for metric storage. And I think that our value against them is pretty clear. So the way that most people use key value stores for metric storage is you have a key that's your metric, and then a timestamp, and then whatever dimensions you have. So your first dimension might be host name, your second dimension might be server type, and so on. Your third dimension might be availability zone or data center. And what you're going to do to query is you're going to do a range scan on that key. And so because it's a range scan, key value stores all do this pretty quickly, but the key is arranged in a certain order. So your filter has to be some metric and then some time range and then the first dimension. And if your filter doesn't involve the first dimension, then at that point you can't use any of the other ones for a filter. You have to just sort of scan everything. The other issue is that it's rare to find aggregate pushdown in these key value stores. What I mean by aggregate pushdown is in Druid, the data nodes all do aggregations, and then there's a final merge on the query node. A lot of times when you're querying a key value store, like Cassandra or other key value stores, there's no aggregate pushdown, and so the raw data is streamed out of the key value store into a query node, and that's really expensive. So it's rare to find aggregate pushdown. It's rare to find secondary indexes, so indexes on dimensions, indexes on those dimensions, things you can use for fast filtering other than just the name of the metric. So let me talk about what Druid actually does do and how it achieves those things. So I'm going to skip this slide because it's just a bunch of words. Druid storage format. So here's some raw data. So in this is metrics that come from, looks like web traffic. So there's a domain, beeper.com and ultra.com. So there's two websites, and there's female and male people clicking on things. And sometimes they click and sometimes they don't. OK, so I guess this is online advertising impressions. So sometimes they're clicked and sometimes they're not. You can tell that I didn't make this example. So these are online ad impressions. And the first thing we do is summarization. So this is really useful if you don't pre-summarize. So for a lot of people doing stuff like system metrics, like if you're reporting them for like time series metrics from servers, those are often pre-aggregated on the node, and so summarization doesn't really do anything. But we do support summarization for other kinds of metrics, and that's really useful if you're not pre-aggregating them. So a lot of people don't pre-aggregate things like web traffic or ad impressions or events like that. And if you know that all your queries are going to be sort of slice and dice, we can pre-aggregate along the things you're slicing and dicing on. So this data set, we're going to be slicing and dicing on domain and gender and hour of time. So all those timestamps have been truncated to the hour. And we've rolled, we call this rolling up or summarizing. We've rolled everything up into 3 rows instead of however many there are on the left side. We're still here enabled to do any query that's in the form of grouping on any dimension, filtering any dimension, so we can still do anything other than just dumping the raw data. And actually, in the next version of Druid, we're making this optional if you do want the raw data, but it's not been an option until now, just because for most Druid use cases, slicing and dicing summarization is actually really useful. The next thing we do is we segment the data into segments that are time partitioned. So in this example, these segments are partitioned by hour, and we have 1 data point in the first, 2 in the second, and 1 in the last one. In the real world, these segments would all have millions of data points in them. And they're time partitioned such that they can be pruned more easily for when you have a time filter. These segments are all immutable. They're the fundamental storage unit in Druid. Because they are immutable, there's no contention between reads and writes because there are no writes. And we have a concurrency model where the queries, one thread is scanning one segment. A segment can be scanned by as many threads as you want at a time. And so that really lets queries operate at maximum speed without any write contention. And we do support writes, obviously, because the database is useless if you can't write to it. But I'll talk later about how we do writes in such a way that we still don't have read contention for most of your data. This is a slide talking about how we store things in columns and we dictionary encode. I'm going to kind of skip past some of these. I think we're running low on time. But this is pretty standard for column stores. So if you're familiar with like the Parquet format, for example, or ORC on Hadoop, they do similar things. This is something that is a little more unique to Druid. These are the indexes that we do. So this is something that Parquet and ORC don't do, and that a lot of key value stores don't do, which is have indexes per column. And we use these for Boolean filters. So if you say, I want to find all metrics where the node type is web and the availability zone is US East 1A, then we can pull an index for web and pull an index for US East 1A and combine those indexes, and then we can scan only the rows that we know are going to match that. Finally, another thing that Druid supports is a plugin architecture that a lot of folks have used to build plugins for approximate algorithms. So these approximate algorithms are one of the things that Druid's known for. One that we've supported for a very long time is hyperloglog, which is an approximate distinct count. It's actually a really popular approximate algorithm. It's supported by a lot of databases. One that's more unique to Druid is theta sketches, which is approximate set operations. So while hyperloglog supports union, theta sketches support union, intersection, and set difference. And those can be used for funnel analysis and behavioral analysis in a way that hyperloglog can't, because you need operations like difference for that. And finally, we support approximate histograms and quantiles, which are really useful for stuff like server latency and finding 98th percentile latencies, 90th percentile CPU use, that kind of stuff. And this is computed in a way that even works across nodes. So one thing that kind of sucks about the way that a lot of people do 90th percentile latencies is you have every node compute its own 90th percentile, and they do that with like a HDR histogram or something. And then they report that as a number to your metrics collector. And then how do you combine numbers from different nodes? There's like not really any way to do it. You can average them, but averaging 90th percentile latencies is not really an operation that makes a ton of sense. So the way that we do it in Druid is we actually keep things in this sketch form until the very end, and so we get more accurate inaccurate numbers, more accurate approximate numbers. But we at least use the same approximation through and through. So these approximate algorithms, which again are something that Druid's known for, are very powerful for making fast queries. And approximate histograms don't have any error bound on them. They are in practice. It depends on the dynamic range of your data. Theta sketches and hyperloglog do have strict error bounds that you can look up on our documentation. You can also write your own plugins, and a lot of people have. Theta sketches actually started as a community contribution from Yahoo. They were using it for behavioral analysis. So the last thing I want to talk about with architecture is how we do writes. So I said earlier that we support streaming writes. We can do 3 million writes per second is the highest that we've seen. But I also said the data is immutable. And so how does that work? The way that works is we have a set of processes in the Druid cluster that all they're doing is ingestion. So most processes in the Druid cluster are what we call historical nodes. And historical nodes are just reading immutable data. There's a smaller set we call real-time nodes, and the real-time nodes are reading current data. And so if you have a cluster that stores a year of data, most of that data, the vast majority of it, is going to be immutable on historical nodes. And a little slice, maybe the last hour or so, is going to be on real-time nodes. And the way real-time nodes work is they do writes into just this really simple hash map in the Java heap. It's like literally a Java concurrent hash map. They actually think it's a concurrent skip list map, but whatever. They only have a time index. They don't have indexes on specific columns, but that's okay because it's small. There's only usually a few 100,000 rows in this map in the Java heap. What happens every 100,000 rows or a few minutes is they're flushed to disk in the Druid segment format, so that at that point they get the column orientation, they get dictionary encoding, they get compression, they get indexes. And then hourly, we merge and compact those and push them to historical nodes. And historical nodes just get those, and then they serve queries on them. So this is an append-only system, and that's how real-time writes work in Druid. They work in an append-only fashion. If you want to replace your data, you can, but you do that with a batch process. We don't support stream updates or stream deletes, just stream appends. But the nice thing about that, it's less flexible because no updates, but it's great because it means we get to have the vast majority of our data be super fast to query. This is what the architecture ends up looking like in a cluster. You end up having a lot of historical nodes. You end up having broker nodes, which are our query node. That's where queries come in. And you end up having these real-time nodes that get streaming data and then push segments to historical nodes. And the broker queries both the real-time nodes and the historical nodes. So for deploying Druid, it integrates with a variety of stuff. Most of the stuff we integrate with is open source because Druid's open source, and open source stuff likes open source stuff. So the big thing we support for ingestion, we support a lot of stream ingesters, but the big one is Kafka. We have the most robust support for Kafka. We recently added an exactly once transactional loader from Kafka. We also support a variety of stream processors where you can push directly to Druid or go through Kafka using Spark Streaming, Storm, Flink, Samza, and a few others. And we also support batch processors. You can load from Spark in batch, or you can load from Hadoop in batch mode. And those batch loads are what you're going to need to do if you want to replace data. There's a variety of ways to query Druid. So you can query Druid using JSON over HTTP. We have a SQL library as well, R bindings, Python bindings, Ruby bindings. There's also open source UIs. I showed you Pivot, and Caravelle is another one from Airbnb. So Pivot's very sort of exploratory, click around, slice and dicey. Caravelle is a lot more like build a visualization and build a dashboard. So the company that I started around Druid, Imply, we have a quick start for Druid, and also all the Imply stuff. We have a Docker image, and we are also hiring. If anyone wants to work for us, it's sort of the obligatory thing at the end of the talk.